What are you checking? Like which point?
Let's go with 1/2.
1/2's the only issue, right? Because you basically have a line and a sine graph, both of which are continuous, but it's the, are they going to join or not?
Doesn't look like it. No.
Doesn't look like it, does it, right? So you've got, from the left, it's the sine graph, and so sine of pi over 2 is 1, and then from the right, it's that line, and so that would be, what, 4 for the y behavior from the right? So obviously those, 1 and 4 are not the same. And so one of the things about doing a definite integral is the function you're dealing with has to be continuous for you to be able to use a definite integral to calculate, area or, whatever it is we're trying to calculate. There we go. And so we need a workaround for this. And to work around this, we need to be able to work with this piecewise function. We can still do this. What do you think we should do to make this work? Because as it stands, since it's not continuous, we really can't do that integral, really, honestly. What could we do to work around that?
Break it into two.
Break it into parts, right? That's exactly right. So the parts would then have to correspond with the piecewise domain parts. And so I think my first integral would have to go from, what is the deal with this? He also uses my pen, and I feel like it doesn't work now. He gets in my desk. And he takes my pen. And now it doesn't work. There we go. Now it's kind of working. Okay, so 0 to 1/2, right? And of course, that would apply to just the sine part. So sine of pi x dx. And then I would add to that, oh, it's not, there we go. I'd add to that the integral from 1/2 to 2 of the line, negative 4x plus 6 dx. And so now those two integrands by themselves are both continuous, and so we can do a definite integral with those, but placed together, we really couldn't do that. We had to split them apart. Does that make sense? So I've overstepped my bounds just a little bit with that first integral. I hope you can forgive that. You notice it's composite, right? It's not just sine of x, it's sine of pi x. And so, for our day today, I don't know that I would expect, for most of you I would expect you'd be able to recognize this or understand this. What I would do with that first integral is say, the integrand is composite, and so the derivative of the inside has to be the other factor within the integrand. So what would be, just for the first integral, what would be the derivative of the inside of the composite? Pi, right? So this is kind of referring to what I was talking about the other day. The derivative is pi, and it's not there, so this is where Timmy messed up, and so we need to fix the blunder by Timmy. And so what I'm going to do is I'm going to multiply the inside. Okay, this is really bothering me. I'm going to multiply the inside by pi, and of course I can't just do that. I have to also balance that, right? So I multiply the outside by 1 over pi, like so. Okay, so from there we do our antiderivatives, we do FTC1, and we complete the process. So what happens here, of course, is the pi just goes back inside. I'm left with, what is the antiderivative of sine? It's either cosine or negative cosine. Do you remember which one it is? It's negative, yeah. So we'd get negative 1 over pi cosine of pi x, evaluated from 0 to 1/2. And then over here, this integrand was quite a bit easier. And I left the negative off, or it just didn't write. Oh, there's a tiny dot there. There we go. So we just do the power rule. So negative 2 x squared plus 6x, evaluated from 1/2 to 2. Make sense? So I put this in here. I put this in here to remind myself of something, and maybe remind you guys or let you guys know something that, like on an AP test or one of my tests, there would not be a ton of these types of questions. We'll take this all the way through and finish it. But let's be honest, like the first integrand takes a little bit of thought. Second integrand takes a little bit less thought. But as we finish this out, it's going to take a lot of effort to keep all the details right? And so you're not going to see a ton of these. But in the past couple of years on the AP test, you've seen at least one of these on the free response, where it's like mildly complicated. You got to kind of have your stuff together and finish it all the way through, keeping the details right. And so, yeah, don't plan on like a test full of these because it would just take way too long. But don't assume that there won't be any of them. There probably will be one of them that you'll have to handle. Okay, so let's do FTC 1 and see if you guys can remember the unit circle, which I know. Yes, you giggle. So it'd be cosine of pi over 2 minus negative 1 over pi cosine of 0. And then we'll add to that this other stuff. Let's do this other stuff. I don't know if we can do it in our head or not. If I plug in the 2, what do you guys get when you just evaluate at 2? Negative 8 plus 12, right? Okay, so 4. And then minus, you evaluate at 1/2. Let's see here. So you get 5/2? Negative 1/2 plus 3, right? 5/2? Okay. So minus 5/2. Okay, let's do our unit circle stuff. What is cosine of, I'm sorry, McKenna, go ahead.
So, like, if this was on the AP test, you could just leave it like that?
On a free response scenario? Yeah,
Okay.
you
so
definitely could.
Basically, well, you need to know the unit circle, but for that,
Oh yeah, if you don't know the unit circle, you're going to get docked multiple
yeah,
times.
but you don't have to, like, go any further.
Yeah, on a free response, yeah, like cosine of pi over 2 is considered a numerical answer, and going beyond that is just considered simplification, and so it's okay. But do keep in mind, like I've said before, sometimes you'll use these later, and either one of two things will be true. Either the using of it, like it's just kind of a long expression, and so you might lose something, or you might actually have to make a judgment on it as to whether it's negative or positive or bigger than this or smaller than that or whatever, and this will be difficult. But your point is well taken, for sure. So let's try it. Cosine of pi over 2 is 0. That's kind of nice. The whole first term goes to 0. What's cosine of 0? 1. So we end up for this whole first expression with just 1. I'm like really honestly trying to write. 1 over pi. There we go. And then 3/2? 3/2. Is that what I said? 3/2? Okay. So 1 over pi plus 3/2. So anyway, good warm-up, hopefully. A little arithmetic. Get the blood flow into the brain. We all good? Okay. Any questions at all? The piecewise thing makes sense. Why we had to split it, I just want to make sure we're all okay. Okay, fair enough. All right, well, let's move on then. Let's take a look at the average value of a function. What this really means. We just did averages in Algebra 1, and they knew this, so I'm sure you know this for sure. In general, how do you find an average?
Sum divided by the number.
Yeah, sum divided by the number of things, right? Sum things up. Okay. So what is an integral, really? We talked about this in like sections 4.2 and 4.3. It's an infinite summation. I probably should put a definite integral, is specifically what I'm talking about. So an integral is an infinite summation. So then when you think about what you said about how do you find an average, well, it was, well, we need to add stuff up and then divide by the number of numbers. So then to find the average value of a function, we need to kind of do this, but when you think about this, it gets really tricky. So if I had some function that did, this, and here's my interval from A to B, and I said, all right, well, from A to B, I want to know what the average height or average value was. This gets really tricky because how many things would you have to add up to truly get a sum of all the different heights? Wouldn't you have to do it forever? Yeah, there's no way you could say, all right, well, let's start at A and then A plus 0.0000001, right? There's not enough zeros in the world to get all of the different heights. And so when we try to add up all the different y values, this should bring to mind, all right, it better be an infinite summation because there's no way I can mechanically add these things up. There better be a trick to it, like a definite integral. So to find the average value of a function, the first thing you need to do is add everything up on the particular interval. So that's how the function That's the function's purpose here, or that's how the function, you can add it all up. That's what the integral's purpose is, right? To add up all these heights, and that will provide us with the sum of all the y values. But now we need to divide by the number of numbers, and we run into a similar issue, right? Like how many different numbers could you add up as you go all the way across the picture? The answer, of course, is there's an infinite number of numbers between any two real numbers. How are we going to do this? We simply divide by the width of the interval. And so I'm just going to put out here on the front 1 over b minus a, where b minus a is the full width of the interval covering that distance. So we take the sum of all the y values by using an integral. We divide it by the width of the interval, telling us, all right, well, here's what the average height is. And literally, that's what it is. If we looked at this graphically, if I were to say that, there's my function right there, and I have calculated the average to be right here, what would you say? Like that, whatever that y value is in the red line, that's my average value. What would you say to that? Is it good, bad, or confusing? It's very bad. Why is it very bad? Where would the average, let me ask you this, where would the average have to lie with respect to the graph of the curve? Yes, somewhere between the high and the low points, right? So similarly, if I were to say, yeah, my average is up there, you'd have to say, no, I don't think so. That would be like me saying, I play basketball and I average 75 points a game, which would just be a ridiculous number of points to average in a game, right? But you're like, all right, I'll show some respect, and okay, I'll believe you. But then you show up and like the top score I ever score is like 12. You're going to be like, I think you don't really understand an average, or you're lying. One of the two, right? So you would expect that if I did have an average, that it would lie somewhere in the middle of my high and low points. So something like that would be a reasonable representation of an average, right? Darian's like, I average 75. Cameron's like, well, I average 76. Something like that. On the effort scale, right? At least a 76 out of 76, right? Yeah, that's right. Okay, so anyway, finding the average value. Really what this comes down to is remembering a formula. And the point of the last 2 or 3 minutes of me talking about this has been to try to help you remember what the formula is, so that when you get to one of these questions, you're like, oh my gosh, what's the formula? I don't know it. You can say, oh yeah, average. Add things up, divide by the number of numbers. That's really all it still is. So that's kind of the idea here. So I want to give you another chance to do some integrating and anti-differentiating. If you would, apply that formula, what we have right there, to our example, and take it all the way through by hand. Don't, wimp out and do Math 9 or anything like that. We'll get to that in a second. Just try to do the mechanics of it and get all the way through it. And we'll talk over the details in a second. With this, like, what did your original setup look like? Okay. Okay, so, I mean, if you're looking at it and you're thinking, gosh, that's just a formula, you're right. It is just a formula. It's good to know where it came from, and it's also good to try to execute it as well. So Sean has set us up for success. Let's take it one more step here, Sean. Obviously, 4 minus 1 is 3, so we could do that. But we probably should do the antiderivative, right? So what did you get for an antiderivative?
X cubic minus x.
Man, whoever wrote this was really nice. All right, evaluator from 1 to 4. Okay, so Sean, you're good? That all makes sense? Okay, Caleb, why don't you take us the rest of the way? We plug in the 4 and the 1. Let me ask you this, Caleb. What did you do with the 1/3? Did you kind of leave it out of the FTC one, or did you left it out?
Yeah.
Okay, that's fine, of course. So let's do it that way. So 1/3 gets left out, and then you plugged in. How'd that go?
So I plugged in 4 to the x cubed, which was 64, and minus 4 squared is 16.
Got it?
And for the second part of that, I just got 0 because it's 1 minus 1.
Yeah, 1 minus 1. Okay, so what do we do with that 0, though?
Just leave it out. I wrote in minus 0.
Okay, sure.
So
Okay, so you're saying that you could just like not even bother to write it?
Yeah.
I'm fine with that. Okay, so then you finish out the arithmetic, and what'd you get?
48 over 3, or 16.
16. Yep, very good. Okay, yeah, perfect. Great job. The numbers turned out nice. whatever. Do you have any questions? Everything's going okay? All right. Good deal. Let's move on to our other topic here in regard to average value. Yes, so this is the mean value theorem for integrals. And this is kind of the thing that I was hinting at earlier. If someone claims to have a certain average anything, then you should be able to observe them and see that not only is their average, within the minimum and maximum, but if they have a continuous set of data, then they should actually hit that average, right? And so this is where, we'd want to think about this. Let's say we go back to the basketball example. Let's be a little more realistic. Let's say that I told you that I played basketball on the team and that I averaged 15.2 points a game. That'd be a pretty good average. It means I'm scoring quite a bit. But 15.2 points. You stop to think about that for a second. There's no way to actually score 15.2 points, right? There's no way. And so, if you were to say, all right, fine, you score 15.2 points average per game, I'm going to show up and I'm skeptical or I'm going to support you or whatever it is. And I'm going to watch and observe how you score, right? So let's say that, say you show up the first game, I score 13, next game I score 12, next game I score 18, game after that it's 16, then a 10, then a 19. Would it seem reasonable that I average 15.2 points per game? Would you doubt that based on your observing me? Do those numbers seem to make sense? But I never actually scored 15.2 points, right? Why would that be? Why is it impossible? Yeah, you can't score like half a point or whatever. And so would it be fair to say that if we looked at a graph of the number of points that you could score in a basketball game, that graph would be, think about calculus, think about what we're talking about, not continuous, right? Wouldn't it almost be like one of those greatest integer function sort of things? It would just sort of like step up and step down. Wouldn't there be like vertical gaps all over the place? Because you can't score 12.3 points. And so like the idea that you could show up and watch me score 15.2 points doesn't really make any sense because it's not continuous data, right? Think about it like this. Wouldn't game time, like the time that you played in the game, be a little closer to continuous data? A little closer, right? Because you measure down to the seconds, right? So it's like fractions of a minute. So let's say, I got an average. I said, hey, I do play on the varsity team and I average 10 minutes and 30 seconds a game. You're like, okay, fair enough. Could you show up and probably watch me play and, if you're like a total nerd, like record the times that I'm in the game and how long I was in the game? And would it be conceivable that you could see me play for 10 minutes and 30 seconds, right? And so if you have continuous data, then you should be able to see somewhere where the curve hit the average, actually met the average. That makes sense? And that's what the mean value theorem for integrals is all about. The condition is continuity. If the function we're dealing with is not continuous, then this whole thing is, there's no guarantee, right? It's not for sure that you would actually fulfill the theorem here, the mean value theorem for integrals. And so we see this right here. This piece of the puzzle right here, this is a little formula. And of course, you recognize the left side. Isn't that the mean value? Isn't that the average value of a function? And so what that is basically saying is that the average value of the function equals f of c, where c is somewhere on the interval. So in other words, if you have an average and the data you're dealing with is continuous, then at least one time you will hit that average on the interval. And so the graph that we looked at earlier, I think applies here. If we had a graph, again, continuous graph, and did something like that, there's A, there's B, right there, then wouldn't it make sense that my average would have to be somewhere in the middle, like let's say right about there? Well, if that's the case, do you see how at least at one spot, two spots, possibly a third one on the far left, at least two spots I've hit my average? And the contrast with this is the ridiculous thing would be for me to say, there's my graph, yet my average is up there. That makes no sense. It has to be somewhere in between. And not only that, if the function is continuous, I actually have to find an intersection point between the average value as well, between the average value and the curve. Make sense? Okay. And that's what that formula is trying to describe. In other words, somewhere the average, or I guess I should say instantaneous height equals the average height. the instantaneous height or the height at one particular point will have to equal the average height somewhere, at least one time, as long as the function is continuous. And if you feel like I keep saying continuous repeatedly, I am. I'm doing it on purpose. That's the condition for the theorem, and so we want to make sure that we understand that condition before we proceed with any sorts of questions like this. Okay, so once again, I've been really fairly somewhat nice to you with numbers. If you guys could take a look at our example here, it says, find the average value of the function on our interval, and then find all values of x on the interval for which the function equals its average value. Notice the words mean value theorem for integrals are nowhere. Those words are nowhere in this question, but the last part is the mean value theorem for integrals. Find all values of x on the interval where the function equals its average value. That's the theorem put out there. Does this function meet the condition? Is it continuous on that interval? How do you know? Polynomial, yeah, of course. Okay, so check it out, try it out. We'll go through it together in a second. Okay, so you said integral from -1 to 2, and I kind of lost you after that because my...
I said multiply it by 1 over 2 minus -1.
Okay, 1 over 2 minus -1. I like it. And then we just do the function in there. Okay, so 4x cubed minus 3x squared dx. And is that kind of where you started right there? Because it did say find the average value, so I think that makes a lot of sense. How'd the numbers work out? Were they okay? They get kind of, they all right? So x to the fourth minus x third would be your antiderivative. And we do FTC 1 here. Cameron, what'd you get? Like when you plugged in the 2 and plugged in -1 and subtracted and all that stuff.
I got 4/3.
You guys agree with that? Arithmetic, 4/3?
Something else because I checked it.
6, you got 2.
Yeah.
So let's see here, it'd be 16 minus 8 minus 1.
Minus -1, just 2.
Let's see here, let's just look at it real quick. So 1/3, and then here would be 2 to the fourth is 16 minus 2 cubed is 8 minus, that would be 1 minus -1. So 8 minus 2, I agree with you there. 6 over 3 is 2. Is that all good?
Yeah.
Awesome. Okay. So then what is that? Like what's the meaning of that number?
The average value of f of x.
Yeah, the average value of f of x on that interval, right? So we've done the first part. Then it does go on to say, find the x value for which the function equals that average value. So now there's kind of another step, right? Caroline, how'd you set that up?
I set 2 equals f of x.
Yeah, 2 equals f of x. Or you could write f of x out if you wanted to, but that's totally fine. So we're basically saying that the output is 2, or the y value is 2, and we want to know what the x value is. So Caroline, did you also turn to the calculator?
Yes.
I think that makes sense, right? I mean, it's a cubic. Nothing really factors out. Yeah, I think that's probably the place we'd go. How many answers did you get?
1.
1? What was it, Caroline?
1.137.
All right, with 3 decimals and everything. You guys agree? Okay. And of course, this is cubic. This cubic, let's see here. Did it did it have turning points? Did you look at the graph?
It did.
Like barely though, right?
Yeah, it was before 2 though, so.
Just something like that.
Yeah.
And so then your average value is 2. And so, like right in there somewhere, I don't know. And so we basically found that intersection point. What would be the coordinates for that particular intersection point?
1.137,
Comma 2, right? Yeah, the comma 2 is the part that might be so obvious that it's hard to see, right? It is 1.137 approximately, comma 2. All right. Doing okay? Fantastic. By the way, chapter 4, which is what we are doing right now, is the only chapter this semester that doesn't have any new stuff or outside the box stuff. So I don't know if that's comforting or disappointing, but this is how it is. So let's take a look at number 2. I skipped over the video material. The video material is about FTC 2. So remember, there's 2 parts to fundamental theorem of calculus. And if you read other math books, some other math books call our FTC 2 their FTC 1 and our FTC 1 their FTC 2. Some books just say that there's an FTC. So just know that this convention of 1 and 2 is kind of your book, and other books too, but not all books would name things the way that your book has. So for whatever that's worth. The bottom line is the meaning of FTC2, or the kind of the thrust of it, is that the derivative and the integral cancel each other out. That's essentially it. There's details, of course, but that's essentially it. So if you take a look at an example like number 2, number 2 is challenging because if you didn't know FTC2, you'd get really stuck. Why would you get really stuck? Some of these you can do mechanically, like you can go through and do all the little steps without knowing FTC2. Why would this one not work if you just tried to like muscle your way through it?
The variable and the integral,
Specifically,
the x squared, the
so you're saying like this guy right here? Oops. You could do that. Like, check this out. I'll show you. Can I show you a counterexample? Like, let's say we had the whole different question, of course. Let's say we had integral from 2 to x squared, and let's say it was sine of t. Then what I could do is I say, you know what? Let's make it a little bit easier on ourselves. Let's say it's cosine of t. I could say that the antiderivative of cosine is sine, so it'd be sine of t evaluated from 2 to x squared. So I'd get sine of x squared minus sine of 2. And while that's not some number, it's not like a constant, it's doable, it's an expression, it might mean something, right? So it's not really, I mean, the x squared might help us identify what the question is trying to test you on, but that's not the problem. It's the t cubed, right? What's the problem with the t cubed? Why is that such a big deal? Are we anti-cubed?
It's composite.
It's composite, and
We don't want to.
yeah, U substitution will not work. Timmy has messed up beyond anything we can fix. So we have to look at that and be like, well, of all the ways that we know how to evaluate an integral, find an antiderivative, none of them are going to work here. None of them. In fact, I don't even know. And if somebody forced me to do this one, I would probably make a series out of it and approximate the answer to an acceptable level of error, I suppose. It's a mess. It's a horrible mess. And so my point being, we really have to use FTC2, the kind of the trick. So the way you do that is this. Number one, you recognize that it's FTC2, and all the elements are there. Caleb mentioned the x squared as kind of being a hint, you know, that's kind of what they're wanting to test you on. And then also, of course, they're doing the derivative of an integral. If you're doing d dx of an integral, it's like, this might be FTC2 somewhere in here because that's kind of the basic thrust of FTC2. So here's the trick. If you watch the video, hopefully, or if you remember this. All you do is you recognize that these two things, the integral and the derivative, effectively cancel each other out. The x squared gets dropped in wherever you see a t, and the dt goes with the integral as well. The x squared gets dropped in there with where the t is, so it would be cosine of x squared cubed, which would be multiply, right? So you get x to the 6th. But there's one last little trick. It's because of the chain rule. What do we have to multiply by?
The derivative.
Derivative of what you plugged in. Derivative of x squared. So in this case, it would be times 2x. And you're done. So like if you can recognize it more or less as fast as you can write and calculate a fairly simple derivative, you're done. Instead of really just banging your head against, how do I find the antiderivative when the answer is kind of you can't. We'll just do this. Hope that makes sense. Okay, so let's look at a little application of that. Calculator is active here. And number 3, so it says if f of x is defined as an integral from 2 to x of sine of t cubed, find the critical numbers of f of x on the interval from 0, open interval, from 0 to 2. And so I would expect, to be honest with you, like if you think about this, I'm peeking over Darian's shoulder here. He has shown some work. Good. I would definitely expect to see a certain level of work, and he's got it. And I'll kind of explain that to you. But then once you get to that certain level of work, then the calculator is going to be extremely handy here. So give it a shot. Yeah, let's remind ourselves about critical numbers. Critical numbers are places where what happens?
Where f prime equals 0.
Or
Doesn't exist.
We probably won't run into that issue here because we obviously have a sine function, so I don't think that's going to be a problem. But where f prime is 0. So if we're going to find f prime equals 0, we probably should know what f prime is. And it's not given to us directly. And so this first step is really why this would be in this part of the book, or in this part of our notes, right? So to find f prime, you need to differentiate the left side. But then, whatever you do to the left side, you got to do the right side, right? So if you probably just recognize this, but if you didn't, you could maybe write this. Okay, let's differentiate the right side. And when you write it out like that, doesn't it look just like FTC2? So I differentiated the left side, I differentiated the right side. Hopefully at some point in there, whether it's just up here or on your paper, you'd recognize it and be like, okay, I know what this is. So then f prime of x, of course, would equal sine of x cubed, and then technically times 1. Right, multiplying by that chain rule factor. Of course, you don't have to write that. But just saying that d dx cancels out with the integral, and you're simply dropping the x in there where the t is. That's our f prime. So we'd set that equal to 0, recognizing that it's always going to exist. Setting that equal to 0, definitely calculator time, I would say. You could do it without a calculator. You'd end up with like cubed roots of some stuff that would maybe, I don't know, less than pleasant, I suppose. It'd be hard to identify if it's between 0 and 2 for sure. So how many did you get? How many answers did you get when you used the calculator?
2.
2? What'd you get, Alyssa?
1.465 and 1.845.
All right. 1.845. Do you guys agree with her numbers?
Yes.
Okay. You definitely could use the calculator here. Would not expect you to place those in the interval 0 to 2 with cubed roots and pi's and stuff like that. So, all right. Still doing okay? All right. Fantastic. Moving on. Yes, this is the final topic in 4.4. We're doing really good. This is called the net change theorem. This is where we get to do some pretty fun applications of things that get fairly realistic. And so here we go. The concept here with the net change theorem is that the definite integral of a rate of change will give you some kind of an amount of change. So this is where the semantics of rates and amounts and the units that go with those, pretty important to distinguish between those things. And we'll want to work on describing what they mean and all that kind of stuff. So for example, if you look at the first integral there, the integral from a to b, I'm just doing units here, of miles per hour dt. Well, the t has a meaning, right? The t is time, presumably measured in hours. And recognizing that a definite integral is simply a summation, right? Simply an infinite summation. Wouldn't the hours and the hours, as far as the units go, just cancel out? All we're really doing is we're summing up a certain number of miles. This would give us a distance measured in miles. Similarly, a leaky tank. I mean, if you've done calculus for any length of time, you've seen a tank that's either being filled or leaking or both at the same time. It's just standard practice. If you do a calculus class without a tank being filled or leaking or whatever, you didn't really take calculus, I don't think. I'm being silly, of course, but they're very common. So once again, the dt would be measured in seconds probably. It's a time representation, so the seconds would cancel. And so even though we were doing the definite integral of a rate, gallons per second, it'll end up giving us an amount of change measured in gallons. So the difference between a rate and an amount. Silly as it sounds, people mix them up. But wouldn't it sound silly if you asked me how far I lived from Valor and I said 10 miles an hour? But questions get answered like that all the time when you're not careful, right? Or if I said, how fast can you ride your bike? And you said 20 miles. It's like 20 miles per hour, or you rode it for 20 miles, right? So the units and the semantics need to agree what we're talking about, and they're different, right? A rate and an amount are just different. They're related, but they're different. General principle, the integral from a to b of some rate is always going to give you some kind of an amount, and I'll be specific here, an amount of change. How much, whatever it was, changed. I'll give you a real general one here. Check this out. If I said the integral from a to b, and the integrand was f prime of t, dt, here's where this comes from. Wouldn't it be fair to say that f prime is some sort of rate? Because the derivative is a rate of change, or it's a slope at a point, or whatever. It's some kind of a rate. So using FTC2, what would the interaction be like between the integral and the prime? Cancel each other out, right? That's FTC2. So this would equal this right here, f of b minus f of a. And over here on the right side, I feel like we can look at that and say, all right, well, that's an amount of change, right? It's the amount at b minus the amount at a, literally giving you an amount of change. You know, like if somebody were to lose weight, they used to weigh 150 and now they weigh 145. To find the amount of change, you would subtract 150 minus 145. If somebody's bank account increased from 1,000 to 1,500, to find the amount of change, you'd go 1,500 minus 1,000. You know, you get it, right? And so the concept of f of b minus f of a gives us that amount of change. Okay, so take a look at example 1. Gasoline flowing out of a storage tank. Yes, there we go. Yeah, thankfully it's not leaking. Someone is just pumping gas into their car, hopefully. Yeah, so gasoline flows out of a storage tank at that rate r of t. Find the amount of gasoline that flows out of the tank from t equals 2 hours to t equals 7 hours. Quick. Setup-wise, Darian, what did this look like for you on a setup?
It'll go from 2 to 7 of r of t, or 5,000 minus 2t squared.
Sure, totally. Of course, you can't always use r of t if it's named.
Right.
You can definitely do that. Okay, so he's got the exact right setup, and you know the details are not too bad. Of course, you'd get 5,000 t minus 2/3 t cubed when you did your antiderivative.
Yep.
Evaluator from 2 to 7. Darian, did you take it all the way to an answer?
I did. Did you just want the exact answer?
Yeah.
Or an approximation, either one.
24,777.
Is there some decimals in there? Let's go 3 decimals.
Okay, it would be 776.666.
Okay. I guess that makes sense with the third there.
Right, yeah.
Okay, good deal. Do you guys agree with that number? Okay, good deal. And what units would go with that?
Gallons.
Gallons, yes, not gallons per hour because that was a rate. This is an amount of change, so yeah, that makes sense. All right, wonderful. We will strive to finish up 4.4 when I see you next time.